later. Let's see, we have spent quite a bit of time talking about band structures, and now we are ready to really look at the primary transport and photonic properties, electronic and photonic properties of semiconductors and their nanostructures. So we did spend a great deal of time. So let's see, today I'll cover two topics. One is, as we have discussed till now, in a semiconductor, after we do all the electrons in a periodic crystal sort of picture, what we end up with is energy versus the wave vector k picture that looks something like this, right? Let's simplify it and look at the conduction band minimum and the valence band maximum. And we label it as E sub c is the conduction band minimum right there. And valence band maximum E sub v there. And this is our gap, E sub g. Right? And the states here are completely filled with electrons in a semiconductor, and the states there are empty. And just to be kind of be a little more complete, the curvatures here go around, and this periodically repeats with a pi over a to minus pi over a, which are the reciprocal lattice vectors in the k space, right? So that's your entire band structure for semiconductors, and so depending upon what model we use, we'll get a band like that and a band like that, say, be it tight binding or other methods as well. Today, two main things we want to talk about are, one is, as it is, this material is going to be extremely insulating because you have a filled band which is unable to carry current, and you have a completely empty band which is also unable to carry current. So this would be highly insulating. This is the exact analog of closed orbits or the noble gas elements, right? Like helium and neon and argon. It's the exact analog. And as you add more electrons, then you start getting metals and so on, right? So that's that. So we have to do something to it to make it conduct, right? So that's so the first thing we'll talk about today is where is the Fermi level of this semiconductor, and we'll have a very precise answer. We'll find a very precise answer. Second is the Fermi level, wherever it is here, probably it will be somewhere in the middle of the gap. And as far as flowing current through it goes, it's going to be extremely difficult if the Fermi level is in the middle of the gap because it has very few carriers to give you, right? So how do you put carriers in the semiconductor? And one of the methods we are going to talk about today is doping. We dope the semiconductor with excess electrons or excess holes. We either fill out some empty bands, and that would be n-type doping, you fill it with electrons, or you empty out filled bands, and that would be holes, so to free up some space for conduction. So that's something we're going to discuss today. And then the third topic is, once I put carriers in the bands, how do they move in response to a voltage or a field or electric field, magnetic field, whichever be it. So how do they respond to external perturbations, right? So actually, is that green light blinking there? Is it on? It is on, right? I could see this. Somehow it won't. Oh, well, I did try this, but it somehow was not. All right, let's see. Okay. Okay, so we'll look at these three things today, and As we move along, we'll see that there are many other ways of putting carriers in a semiconductor other than doping. Doping is you chemically substitute certain atoms with extra electrons or missing electrons, but I can electrostatically change the Fermi level, and that would be gating with an electric gate. Capacitive gating, you can move the Fermi level up or down, and that's the principle for most field effect transistor, where you apply a gate voltage and you move the Fermi level into the band, and it looks like a metal, move it back, it looks like an insulator, and you have on, off, and high conductivity, low conductivity, and so on. So the third method is you can shine light on it, photons. The photons can come in and kick up electrons from here to there, empty out these states, fill these states. So that's the heart of photonics as well. So there are three methods, but we'll look at the passive method, which is doping, which is you just change the elements, the chemical composition. And then later on, we'll look at the active methods, which is gating or photons. Okay, so let's first look at the question of where is the Fermi level. And I was hoping to use the slides. Let's forget about the slides then, because it's I'll try later again. I did restart it though. Okay, just give me one second. Let me try one more time, because there is a couple of things which would be nice to show. Maybe this will work. Oh, wait. All right, this works. Good. So what we want to, I just want to kind of show you where are we on the set of slides, and we are starting to look at, if I have, let's say, the whole band structure of a semiconductor, something like that. In the last class also, I did give you the handouts and indicate that there are only certain regions of the band structure we are interested in most of the time, at the top of the valence band and the bottom of the conduction band. That's where all the action will be. And then we are going to now ask the question, how many, say, electrons are there in the conduction band, and how many electron holes are there in the valence band? And that's what we want to first ask. And that question will immediately force us to first answer this question: where is the Fermi level of the system? So once you find the Fermi level, it answers quite a few questions. How many electrons are there? How many holes are there? How many of them are available for conduction, and so on. So now the way to find the Fermi level is in a semiconductor is always the same trick. The fundamental idea is charge neutrality. So it's obvious. It's actually obvious that the material has to be charge neutral. And so unless you have put some gates on it, or you are injecting electrons into it through electron beam, at equilibrium, the material, the semiconductor, is charge neutral, just as is a metal or an insulator is charge neutral. It has equal number of negative and positive charges. So that's really what it is. Now, what are all the energy states available to the semiconductor, to the electrons in the semiconductor? So I'll actually draw this right next to the band structure. And let's say the minimum of the conduction band here has an effective mass of m star. I'm going to write it as sub c. Sometimes it's m star e for electrons, and I'm writing C for the conduction band. Similarly here, the curvature or the effective mass here, I'm going to write it as m star v. Okay. So these are the notations, and I hope this is very standard now. You can write it this way. These are the curvatures, and these can be definitely different from the free electron mass. For example, typically in a semiconductor, what about m star t? Is it larger or smaller than free electron mass? Typically it's smaller. Just from the perturbation theory analysis, you can show that m star c will be 1 over 1 plus something positive. So it's typically smaller. This will be typically larger. It's the whole mass. It will be typically larger than the electron. So regardless, I mean, there are some cases where this can be much lower too. You know, I mean, I'm not saying it's general. Even actually for narrow bandgap semiconductors, they can also be lower than the free electron mass, the whole mass. Okay, so but if I have a three-dimensional semiconductor, a 3D, you know, crystal of the semiconductor, then the electrons are free to move in 3 dimensions, and you have a parabolic band structure. It starts looking just like a free electron, but with a different mass, right? So we have already found the density of states for such a situation. What is the 3-dimensional density of states? It goes as square root of energy, right? And if I were to write the value of the energy, I'll write the conduction band density of states is equal to, if you go back and check, it's given by twice the mass, but now it has to have the effective mass. Okay? 8 square 3/2 times square root of energy. And what is that energy? It is energy with respect to the minimum of the conduction band. Energy on this axis, but with respect to this is the minimum, right? So you get E minus EC. Right? So that's the 3D density of states, density of energy states that you can have here. But you know, just to be clear, as you go far away from the parabolic approximation, you can see it's curving back around. It's no more a parabola. And the density of states, I think you can tell me what's going to happen. You know, how will the density of states evolve? You know, near the band edge, it's definitely square root, right? But as you go up, what happens? You know, very high up, it will go down and again go to 0 here, right? Because the band ends there, right? So it will kind of go up and then go down here. This part of it, in most semiconductors, would be irrelevant. Most of the times, we'll be interested in this square root increase. You know. But it's there. I mean, the upper bands, they close like that. And exactly in the same way, the valence band will also, this is the bandwidth, will also increase as square root, but then it will also kind of go down. And let me write that down. Valence band density of states is, again, it's like 1/2 pi squared. Generally, there'll be valley degeneracy here if you have multiple valleys. I'm saying this, let's just look at one valley at this point. Mass valence band over h bar square, 3/2 square root. And now you have to kind of, you know, excess energy is downwards, so you get EV minus E. You know, that's just to be accurate. So that's the valence band density of states and conduction band density of states. The way I've sketched it is misleading. Because the mass is heavier, the density of states is larger. You know. It's larger because sitting in the numerator, the 3/2 power. Okay? So it will kind of look something like that. Now, here's a trick question. If I integrate the area under this curve and integrate the area under that curve, which one is larger? They're exactly the same, right? Right? The total number of states here is always the same as the number of atoms in the crystal. So remember that. Yeah, yeah. If it's larger here, then obviously it's, you know, thinner in this direction, so that you can kind of make out, right? So that's how the density of states is going to look. But this expression is clearly not valid for the whole DOS. It's only valid on the top edge and the bottom edge here. Now here there'll be some other band, and let's not get into the details. I'm going to be interested, as I mentioned earlier, this region and this region only. So I'm going to kind of, you know, look at this part and that part. Okay, so now we can ask. That's the number of available states, right? These states are available. So at this energy, I have this much states available. This much states available. But how many of them are filled? You know, that's the question we want to ask now. So that will depend on where's the Fermi level, because the number of electrons in the conduction band is equal to an integral of the density of states of the conduction band times the occupation function of that energy and EC. And I should really go from EC to the upper band edge here, but we'll see that the Fermi tail really dies very fast. You know? So I'm going to put infinity without, you know, and it's perfectly fine. If you have, for whatever weird reason, a very narrow band, then you can't put infinity. You must consider the top edge as the band. But I'm going to now show that this Fermi function is going to look something like this. Let's say the Fermi level is here. We don't know yet. We have to find it by charge neutrality. But let's say it's here. So it's going to be half increase and then kind of become 1. So that's 1 And what I'm sketching here is the Fermi Dirac distribution. EF over Boltzmann constant times temperature. Right? So that's the Fermi Dirac distribution. So if this is the, I'm going to just redraw it a little bit. So let's say there's a tail going down exponentially there, reaches half at EF, and then it's symmetric around, meaning the difference of it is symmetric around, so it kind of will go and do that. Right? So that's how the Fermi function will look like. And the number of electrons, you can see that there's exponential tail decaying here at very high energies. E is much larger than EF, right? Therefore, this factor is very large, right? This factor is very large compared to 1. Depends on the temperature and all that, but in that case, you can take it to the numerator. That's called the Maxwell-Boltzmann approximation of this. But regardless, we don't have to make those things at this point. Here's the electron density, right? Is that okay? If you know where is the Fermi level, I can use this, plug it in here. I know this, just integrate, you get the electron density, right? So that's how EF determines the electron density. You can see right away that if I moved, by whatever means, if I moved my Fermi level from here to here, what will happen to electron density? It'll go up, right? And it'll go up exponentially. In fact, we'll show that. It'll go up exponentially. And that's one of the most important characteristics of the semiconductor. You can change the carrier density in the band exponentially with a linear change in the voltage. So this is a voltage change. That actually is the most important property of a semiconductor, the fact that you can change something by a factor of billion by changing a voltage by 0.1 volt. So it's a carrier density. That's the most important property of a semiconductor that we make use of in a diode, in a transistor, in a rectifier, laser, all that stuff, right? So, okay, so similarly, if I move the Fermi level down, I'll deplete it of carriers. I have very few carriers left here, right? And we'll see an exact exponential expression very soon. Now, what about, so if I were to just visually multiply the two functions, see, what are we integrating here? DOS times the Fermi Dirac distribution, right? So the DOS is increasing, right? The Fermi Dirac distribution is decreasing, right? So if I were to kind of visually multiply it, let me just do that here. So here's the DOS. So if I were to multiply it, you can see it will increase. There'll be a maxima, and then it'll decrease again, right? Right? So in other words, out of all these states available in the conduction band, only these are occupied, right? Depending on the Fermi level. Now flipping the story around with the valence band, what you want to find is, deep down here, for example, Fermi function is 1. Fermi function, yeah, it's 1 here, and it's 0 out there, very far out. Here it's 1. That means all these states are occupied. Do you see? Let's say I plot the whole band. So let's say I plot the whole band. So these states are fully occupied with electrons. You see that? This Fermi function is 1. But as you go up, there's a little tail that drops here, right? So those states are empty. So in other words, here also you have a mirror reflection, sort of, not exactly mirror reflection, but something very similar. But except those are empty states. Does that make sense? Those states are depleted of electrons. Then those are the holes. You don't have those states there, right? So right. And therefore, P, I'll write it as, you can write it, again, I'm just going to notationally write it. The meaning should be very clear. I can start from very large negative energies and stop here. EV, dE, density of states of the valence band. Now, what should I write here? 1 minus, right? So you want to find what's the probability that this state is empty, not occupied, right? This state is empty. So that's 1 minus the probability that it's occupied. Okay. So that's electron density, mobile electron density in the semiconductor, and that's the hole density. And now once we get this picture, the rest of it is kind of, you do some mathematical substitutions and make approximations and all that, but this is the conceptual basis of everything. So if there's any question now, I'd like to stop, because I'm going to move forward very fast from here. So electron density, if I know the Fermi level, and I know the density of states, I can give you the answer right away. Hole density, same thing, right? And these two formula remain valid whether you have a perfectly clean, pure, undoped semiconductor, or a doped semiconductor, or a gated semiconductor, or a semiconductor with light illumination on it. These two formula are always the same, right? So because you see, there's nothing else to do. You have the density of states and you have Fermi occupation function. So the meaning of the occupation function changes when you shine light on it. You kind of have quasi-Fermi levels and all that. But these formulas remain exactly identical. So the Fermi level, if I move the Fermi level up here, it will obviously increase n. It will decrease this. We'll see that right now. So this is a very general formula. And we can now evaluate it. Let's just do that quick. So here, I'll just do this for the electrons. You can kind of do that thing for the holes. So what we have to integrate is, you can either do it in energy space, or you could have also done it in momentum space. I mean, that's OK too. I could have written n is an integral over k states times f of k. That's a very simple expression for the electron density. Does that make sense, what I'm writing here? Divided by the entire volume. Okay, so you kind of sum it over all k states. This is converted into energy. That's all. When the moment you convert it into an integral, you get dqk. Actually, I should have 1 over volume here. Sorry, yeah, 1 over volume times f of k. And in one more step, this is actually the density of states. You get it right away. If you convert from k to energy, you get it right away. So that's just, you're just adding the number of electrons. That's all. So if I do it in energy space, you can see that you will get 1 over 2 pi squared m star c over Planck's constant 3/2. Then you get your square root of energy minus EC times the Fermi function 1 over 1 plus E. So that's a little bit of a messy integral, and the problem is it's not exactly analytically doable. So it's a Fermi Dirac integral. For 3 dimensions, it's not doable. For 2 dimensions, you can do it. Is the density of states becomes constant in 2 dimensions, and then you get a simple integral analytical form. But here you can't. But what we can do is just kind of rearrange this a little bit, and you're going from conduction band edge to infinity, and we can redefine this as so essentially what are we integrating? You get a square root of x and 1 over 1 plus e to the power x. That's the integral, the kernel of the integral, right? So the integral looks like x to the power half over 1 plus e to the power x. I'm just going to write it like that for now. I mean, you can find out which one are the variables and all that here. And you can change this from, the variable integral, you can change this from 0 to infinity by making a substitution like x minus EF and all that. And this sort of an integral is called the Fermi Dirac integral. And it's very important because obviously it controls statistics of carriers in semiconductors, metals, and all systems that have fermions. So the general integral of this form has x to the power j. X to the power j in the numerator instead of half. In 3-dimensional parabolic band structures, you get square root of energy DOS, right? Which is why we got the square root. But in 2D, you will get x to the power 0. Won't depend on energy. In 1D, you will get x to the power minus half. It will decrease, right? The density of states. So that kind of, this is the integral. And sometimes with a couple of things in the front, but generally this sort of integral is tabulated, and sorry, e to the power x minus eta. Okay, so we'll have to we have the Fermi level. So this is again a very general mathematical integral, and if I have an integral of this form, it's not exactly doable, but these are tabulated, or Mathematica or MATLAB. They know these functions. These are like polylog and all that stuff. There's no analytical form. So in other words, if you do that, what you can show, I'm not trying to write this whole thing out, that the electron density is going to be, after some substitutions and of energies and all that, the electron density will be a product of 2 times m star kt over 2 pi h bar squared, 3/2. Okay? So this stuff kind of comes out from all these combinations here, times the Fermi Dirac integral of the, for here of order half times eta, and eta is EF minus EC over Boltzmann constant times T. So you get this full formula for 3 dimensions. This is conduction. And this is an exact relation, saying that here's the Fermi Dirac integral. The electron density depends on temperature here, but it also depends on temperature to this function here. Okay. By the way, these are written out in the class slides and notes, and so please you use that if I make any typo or something. Yeah. So, but this is the nature of the integral. One of the nice things about this integral is if your Fermi level minus EC, if EF is far below EC, right? How far? Many kTs below EC. Yeah? And at room temperature, what is kT? Right. So it's about 26 millielectron volts, MeV. Okay? Millielectron volts, right? Typical band gaps of semiconductor is about an electron volt, or 2 or 3, depends. Silicon is about 1 eV, right? So, and this is millielectron volts. So if you are, you can see if you are half the band gap, that's just in the middle, that's 500 millielectron volts. So that's 20 times that, right? So that means if the band gap, if the Fermi level is 20 kT below, then what is the argument? Minus 20, right? Does that make sense? Let's say EF minus EC is 20 times kT, right? Then the argument, sorry, EC minus EF is 20 times. Let's say, and this is just for argument's sake, kT. Then that's this minus 20, right? So this function, the Fermi Dirac integral, has a very nice approximation that if your argument is much less than minus 1, right? And you can kind of see that right here. If the argument would be much less than minus 1, then the Fermi Dirac integral of any order j becomes e to the power eta. So this is the Maxwell Boltzmann approximation of the Fermi Dirac integral. It's very, very useful approximation. So that's the okay. So just to be clear, this is eta is negative, right? So e to the power a large negative number. So this number is very small. So this, yeah. There's another approximation, which is if eta is much greater than +1, in which case I'm going to just not try to write the exact form, but it goes as eta to the power j plus 1, j plus something like that. So it becomes a power law instead of exponential. I'm just going to kind of leave it like that, something like this. Okay? And that's called the degenerate limit, when the Fermi level, instead of being far below, it's actually in the conduction band. It's far above the band edge. So that's more like a metal, more like a metal. And so that would be called a degenerate limit. We will encounter both of them when we look at the ballistic transistor. When we look at the full quantum model of a transistor, we are going to encounter both of them. We'll see when the transistor switches off, this is what dominates. When the transistor switches on, this is what dominates. We'll see that later on. So I'm not trying to spend too much time on this right now. Yeah. Okay, so let's look at a situation when the Fermi level is indeed far below the conduction band edge. Under that situation, this whole thing in the front is called N sub C. It's called the effective conduction band density of states. It's effective density of states. The full density of states is right here. Right? It's a function of energy and all that. Now this N sub C is called the effective density of states. Why? It'll become clear once I do that approximation. So I make this Maxwell-Boltzmann approximation. I write it as N to the power E to the power eta. And eta is this. And I'm going to write it like this, EC minus EF over KT. Now that's how typically it's written. So that's your electron density in the conduction band. And So okay, this part is what is called the effective conduction band density of states. The reason it's done this way is primarily for an engineering sort of application. What you can imagine is instead of thinking about the whole details of the square root DOS and all that, I can imagine that I have a fixed number of states here, and that value kind of, what I'm doing here is I'm integrating out all these and saying that I'm going to put all of them here in one rectangle, and the value of that is NC. And the number of electrons in the band is the DOS, effective DOS, times an occupation function, which decides how much of them are filled. And that occupation function is just e to the power minus EC minus EF by KT. You don't have to do all this, but it actually immensely simplifies calculations. Physically, the reality is something like this, and this approximation, the non-degenerate approximation, makes it look like I have a constant DOS, and if I want to find how much states are filled, that's the factor. Does that make sense? So that's, and if I substitute typical numbers of say 0.2 effective mass and room temperature, Planck's constant, you will get this is of the order of 10 to the power 18 per centimeter cube. This NC, or this term, is of that order, 10 to the power 18, maybe 10 to the power 19, depends. And based on that, if I tell you where is the Fermi level, you should immediately be able to tell me how many electrons are there in the band now, right? So let's say EC is equal to EF. I know that kind of violates this approximation. But let's forget about it for a second. What if EC is equal to EF? How many electrons are there if the NC is this? It's exactly 10 to the power 18 per centimeter cube electrons. So if your Fermi level goes up right there, that's the order of electron density you're going to get, very close to the conduction band. If it goes far away, it goes down exponentially, and you can see the exponential decay. Later on, what we are going to see is this Fermi level. We will control it in a transistor, for example. We'll control the Fermi level location with a gate voltage. So that's how we can populate or depopulate the state externally through a third contact. So in the exact same way, what we did here, you can find the whole density. And I'm writing approximate, but many times if you open a semiconductor devices book, you'll see it's written as equal, but it's understood. I mean, this is an approximation, and I showed you the approximation. Whole density similarly will be valence band density of states, just like you have conduction band here. Here you'll get m star v, valence band effective mass, times e to the power e minus ev over kt. The minus sign. So here, if the Fermi level is very far away from the valence band, again you have very few holes. Okay, and so this is what takes care of that. EF, if it's larger and far away from the valence band edge, you get less holes, so it exponentially decays. And as the Fermi level goes closer to the valence band and merges with it, this becomes e to the power 0.1, and you get valence band density. This also of the order of 10 to the power 18 or 10 to the power 19 per centimeter cube. So so now with these two expressions, I can take the two and find the product, n times p, and what you will get then is nc times nv, right, times exponential of this plus that, right? Let's see, this plus that means my Fermi levels will cancel out, right? Minus EF and plus EF, right? My Fermi levels will cancel out, and I'll get minus EC minus EV over KT. Okay. Yep, there's a question. Yeah.
Yeah. Is F there correct? So you said that the approximation we're using is that Fj is approximately e to the n.
Eta. Yeah, right.
Yeah.
Yeah, okay, so maybe I didn't. Right, so the way it's defined is EF minus EC here, okay? So and then I switched it for a good reason. You don't have to, you can write it as e to the power EF minus EC, in which case it is indeed whatever sits in the argument here is there. So whatever sits here, there. And that quantity is EF minus EC over KT. Here I have EF minus EC by KT, but with negative sign.
Oh, okay.
Just flipped around here, yeah. But I mean, the reason I did it is because, I want to show that typically if the Fermi level is inside the gap, you have less carriers than the DOS. That's why, and e to the power negative number is less than 1. That's why I just want to show that. And okay. Now, so n times p is equal to that, and you can see now these quantities do not depend on where the Fermi level is. These are band parameters, effective mass, all that stuff, what atoms are sitting in the crystal and all that. And what is that parameter there? EC minus EV. That's the band gap, right? So now you see n times p does not really depend on where you put the Fermi level. It doesn't care about that. It's an invariant as far as where the Fermi level is, Eg over kT. And all it depends on is what is the material it's sitting in. That's all. So this is the equilibrium. This is called the law of mass action. I really don't know why it's called that, but it's probably from chemical reactions and all that. N times P is constant in a semiconductor at equilibrium. And so NC, NV, you can find those quantities from there. And this quantity is typically referred to as Ni squared, an intrinsic carrier concentration square, Ni squared. Right.
What do you call it? Law of mass?
Law of mass action. Maybe this is an old name. People don't call it anymore. So mass action.
And then N sub I is what then?
Yeah, N sub I is the intrinsic carrier concentration. And I'll explain why.
Do you mind just going over again when you move the Fermi level, what happens to N and P?
Yes, OK. So now whatever we have done till now, whatever we have written till now is true for wherever the Fermi level is. Let me say, this is true for wherever the Fermi level is. This is exactly true for wherever the Fermi level is. Going from here to here, we made a little approximation that the Fermi level is far from the conduction band. But here's what we're doing. So if I, let me sketch this picture one more time here, that if I have my conduction band DOS, valence band DOS, right? And let's say my Fermi level is in the middle, then we just talked about the Fermi electrons will be like that, and there'll be holes like that, which will be filled, right? Now, if I move the Fermi level up, and by this much, let's say, then the Fermi tail, I moved the entire Fermi Dirac distribution, which is here. I moved the whole thing rigidly up. So as a result, this function moved like that. Does that make sense? So it just moved up by that voltage, all of these points. Therefore, the occupation function of these things went up, right? Whereas the unoccupation, or 1 minus this, went down. So as a result, what that will do is it will increase my electron concentration, exaggerating a little bit, and it will decrease my hole concentration. Right? And in what ratio? It's always going to be in this way. N times P is always constant. Right? So if I move my Fermi level. Yeah?
Sorry, so why is it that when you apply voltage, you're shifting
the Fermi level? Yeah. We'll come to that at some point. Okay, so I don't have to apply voltage. I think I'm kind of jumping ahead a little bit there. Voltage is electrostatics. Essentially, what we are doing is we are moving in carriers from outside, or doing something, moving out carriers. Doping is something we're going to talk about today, and we'll see why it will move. So doping is okay. So now, if you so essentially, it's kind of a seesaw mechanism. You increase this, but then you lose this. On the other hand, if you move the Fermi level down, you can create a lot more holes, but then you will decrease the electrons. Right? Does that make sense? Yeah. If I move the Fermi level.
If you move it up, wouldn't you increase holes and increase electrons?
No. So that's good point. So let's discuss that. If I move the Fermi level up, so it will increase the number of electrons, but it will decrease the number of holes.
Why?
Yeah, right. So let's look at the expression. Well, physically, why is that? Just to be clear, the thing is still charge neutral. So, and holes, you can think of them effective positive charge. And so on. So whatever increase has come here has come from here, because the electrons didn't come from anywhere else. So the total number of electrons is always fixed. Therefore, whatever electron increase happened here, oh, I see. What you are asking is, why is it then I'm not increasing the hole density?
Yeah.
Oh, okay, good point. Okay, let me just re-answer that. I see. If I was trying to say that if I increase it, then I also increase the hole density, right? And actually, that is incorrect. What I was saying is actually incorrect. Let me explain why. If I increase the Fermi level, as I think also Andre was asking now, how do I increase it? That's kind of the important question, really. If I increase it by doping or by electrostatics, if I increase by electrostatics, by gating, what I do is the increasing Fermi level means somehow I'm putting more electrons into the system. Right? More electrons into the system by bringing it from somewhere else. If I do doping, what I'm doing is I'm filling the band with extra atoms that have more electrons than the rest of the atoms. So for example, in silicon, I replace some of the silicon atoms with phosphorus that has one extra electron. So that's how I can move the bands, move the Fermi level. Without it, I can't move the Fermi level. I have to change the carrier statistics in it. So that's a good point. So these electrons that are increased here do not come from the valence band, but they're coming from somewhere else. So it's a very important point. Okay, thanks for correcting that. On the other hand, so the n times p will remain in this form. Just as an example, for silicon, Nc and Nv are of the order of 10 to the power 18s, both. Band gap is about 1.1 electron volt. And room temperature Kd is 26 millielectron volts. You can plug in all these numbers, and you will get Ni. Ni will be, for silicon, is of the order of 10 to the power 10 per centimeter cube at room temperature. Okay. So, this is, right? So of the order, that's how many carriers you have per centimeter cube. If you have a pure silicon sample with a gap of 1.1 electron volt and effective masses and all that details at room temperature, that's what it means. And just to compare, how many free carriers do you have? Rather, this is the number of electrons you have in the conduction band and exactly equal to the number of holes you have in the valence band. Ni is equal. So if I have an intrinsic semiconductor like silicon, meaning undoped, completely pure, then electron density is equal to hole density is equal to Ni. Completely pure. And then I'm saying for silicon, that happens to be at room temperature roughly 10 to the power 10 per centimeter cube. So that's how many electrons I have in the conduction band, and that's how many holes I have also in the valence band. Right? So the total number of carriers that can contribute to conductivity is actually n plus p, so that's 2 times Ni, roughly, that can contribute to conductivity. Now, just as an order of magnitude, how many electrons do you have for conduction in a metal per unit volume? Typically. Yeah, this is about an electron per atom, so that's 10 to the power 23 or 22. So this is, you can see, is 12 orders lower, right? 12, 13 orders lower. And that's why the conductivity of this material will also be 12 or 13 orders lower than a metal, because these are the intrinsic carrier concentration. These electrons have been generated purely due to heat, because the electrons in the valence band could absorb some phonons or heat and absorb. If you take the temperature away, if you freeze it down to 0 Kelvin, you will see that all of this will go away. It's all because of heat. And you can see there's an activation and it's an Arrhenius relation, right? And the energy for activation is the gap. That's how much electron, that's the energy the electron has to gain to be able to, go from here to there. That's the gap. Does it make sense? Now, from here you can see, it's obvious, but Ni exact expression is Nc Nv square root e to the power minus gap over 2 kT. It's the square root of that. So just to be clear. That's the intrinsic carrier concentration. Yeah.
So when you did the approximation from electron density to this capital N sub C,
yeah,
you said that was because EF is many kT below EC?
Yes.
So when you do the same approximation for P,
yeah,
is that because EF is many kT
above? Yeah. But yeah, good point. So yes, it is above. So essentially we are saying that the Fermi level is kind of far away from the band edges, and then that approximation works. Many kTs far away from band edges. But the reality is it works even if it is 1 kT away. It works pretty well. You can and you don't have to make this approximation. You can do it exactly. It's just you have to deal with this expression. If you're doing numerical work, you don't have to make any approximation whatsoever. But if you're doing design, trying to design a device, then this is very quick, because we can say that e to the power, let's say we're 3 kT away, then it's e to the power -3, and typically device physics, device engineers know e to the power 3 is a very famous number. It's 20 roughly. So you get 1/20. So I know roughly how many electrons. I don't have to kind of go and do the math. I just know. So that's why it's used, this approximation. And it also is very, gives you a clear picture that the carrier density should change exponentially and all that stuff. This gives you that, right? This is not as easily apparent in the buried integral here. It's okay.
Sorry.
Yeah,
So
sure.
And is this equation just assuming a large EG? And you use them both in the same?
No, this, good point. So this equation is, the exact expression will be, NC times NV times 2 Fermi Dirac integrals. That's the exact expression. But when Fermi Dirac integrals, if you're right. So if I see what you're saying. So if the gap is much larger than kT, then indeed I can make that approximation, right? And that's correct. Yeah, absolutely. If your gap goes to 0, for example, for graphene, it's not going to work. And so our gap is only 30 or 50 millielectron volts, which is close to that at room temperature, then it's not going to work, right? So you got to, but this won't work, but this is always exact. No problem with this. Yeah. So this is just an approximation done for ease of use, but it's a very useful approximation. Okay. So NP is equal to that, and now I'm going to talk about a little bit about how do we put. By the way, any further questions? This is actually a very important concept of semiconductors. How do carriers get generated in the bands? And what we are saying is, even if I had a pure semiconductor at room temperature, I do have a finite chance that there will be conductivity because of if the gap is small enough and all that sort of thing. Right? If you have a very wide bandgap semiconductor, instead of silicon, let's say I take gallium nitride, that's 3.4 electron volts. And you will see that when you go from 1 eV to 3 eV, the carrier density will be 10 to the power -10 or something like that per centimeter cube, which means that if you have 1 centimeter cube, there is no electron in it. This is extremely insulating. So the wider the band gap, the easier it is to make it insulating. The narrower the gap, the larger number of free carriers there are at room temperature. So it's harder to make it insulating. So that's why graphene is very hard to make it insulating. I think the joke is 7-Eleven is always open, or on, right? So you cannot turn it off. You cannot make it insulating, right? So, okay, so now let's introduce the second thing. So in other words, how did I find EF? How do I find EF here? I just write charge neutrality relation, N is equal to P, right? That's EF. Because the total number of, well, let's see, there are lots of charges deep inside bands and all that stuff, but they've all been, effectively, they are effectively all balanced out. The only imbalance I might have is if I have some extra electrons or if I have some extra holes, right? So that's what I'm doing now. Saying the charge neutrality is N is equal to P. N negative charge effectively and P is positive charge. Therefore, I can just write NC e to the power minus EC minus EF over KT is equal to, E minus EV over KT, right? And so from here, you can write down that EF will be, just redo this, take the log and all that sort of thing. I'm just going to write it this way, the thing that makes sense to me. So KT by 2 natural log of NV over NC. I'm just going to write it down this way. So essentially what it's saying is the Fermi level is at the middle of EC and EV, EC plus EV by 2, but then there's a little mismatch factor there, and the mismatch factor is the logarithmic ratio of the density of states. So if the valence band has a larger density of states and V is larger, the Fermi level will move down a little bit. If the conduction band is larger, density of states is going to move up a little bit. And I think it makes sense because if the density of states is larger, it can hold more electrons, right? So if the Fermi level was exactly in the middle, I'll have a charge imbalance. It's also the seesaw mechanism again. The larger DOS pulls the Fermi level closer to it. That's what it's going to say. Okay. Did I say that right? Maybe it's minus then. So I just want to make sure. So if my valence band density of states increases, then the Fermi level should go go away from the valence band. It should get away from it to have the same amount of carriage. So actually, I was correct. It should go up. Yeah. I'm trying to avoid doing the math here because I'm just writing this from that that sort of picture. Okay. But okay. So here's how your Fermi level will look for an intrinsic semiconductor. No doping. No doping. And it changes with temperature and all that sort of thing. Okay, so okay. Now we're going to introduce doping, and then ask how do all these things change? That's what. Yeah. Sorry.
Sorry, I'm just trying to do in my mind what you just said. If NV increases, then EF moves further away.
It should go up, right?
Okay,
yeah. Away from the valence band. So whichever DOS starts dominating, the Fermi level moves away from it. So let's say conduction band DOS, I'm going to just is low, and valence band DOS is very high. Then the Fermi level will be somewhere there. Does that make sense? Or, because then it has to populate, right, equal number of electrons and holes. It has to be farther away from the higher DOS state, so that it balances out. Then okay. And you can evaluate all the numbers here, valence band, and you can see at least if NV and NC are exactly equal, it should be right in the middle, right? And that's. Okay, now we're going to introduce doping, and I'm going to do the part of physical. The quantum part of doping in more detail after your second prelim exam. At this point, I'm going to introduce it at the level of saying that this is another way to fill the bands, and how does it change the carrier statistics and all that, and then later on we're going to look at it in a little more detail because when we actually dope the semiconductor, do measurements, you can pick up all the quantum behavior as well. But at room temperature, typically, here's what happens. Okay, so let's say I take silicon atoms, right, and they're tetrahedral. Let's just notationally plot it. It's bonded to 4 other silicon atoms, right, and then there's another silicon and another silicon and so on, right. So that's intrinsic semiconductor. Every atom in a full wafer is silicon, and that's intrinsic semiconductor. It will follow that relation. It'll have 10 to the 10% unit decay. Now, what I want to do is I want to now preferentially populate this conduction band with electrons, and and I want to have n-type conduction. I want to have electron conductivity in this material. So to do that, what I'll do is take this silicon out and replace it with, say, phosphorus, and then. So if I look at, again, periodic table, magnesium, aluminum, silicon, and chlorine and all that. Okay, so this is the periodic table, the row of silicon, right? So to the left is aluminum, to the right is phosphorus, right? It's group 4 and group 5 of elements, right? In periodic table. What does it mean? All this is this thing has 1 extra electron in the outermost orbit, right? Phosphorus has 1 extra electron. You can use nitrogen or arsenic, depends, these have 1 extra electron in the outermost orbit than silicon does. And therefore, or in other words, it has 5 electrons. That's why it's in a group 5, right? It's 5 electrons in its outermost shell. Now, 4 of those electrons will go and bond to the crystal. Right? It'll donate 4 electrons. The phosphorus, 4 electrons will be taken up in forming the chemical bonds with the next nearest neighbor silicon atoms. But there's 1 left over. 1 left over. Okay? So that electron that's left over, and we're going to show, this is what I'm going to show later, has an energy level. Remember, this is an extra electron now. If I had the whole silicon wafer and I plugged out 1 silicon atom and put in a phosphorus atom there, then that crystal has one extra electron compared to the crystal which had no phosphorus atom, right? It's very important to note that. Therefore, this cannot be the whole band structure. There must be one extra energy level somewhere, right? Where does that lie? For that phosphorus atom, what we will call as a donor, a good donor atom, it should lie very close to the minimum of the conduction band, very, very close. How close? Perhaps a kT or lower. So that that electron that is supposed to be bound to the phosphorus, because it's sitting in a lattice and it has to have this kT energy, it gets, basically the electron gets kicked around with the energy of kT if it's in a temperature T, in a crystal of temperature T. That energy kT should be able to kick it out and put it in the conduction band, and that electron is not bound to phosphorus anymore. It's free to move in the crystal now. Yeah? So that's the meaning of doping. So this electron, ordinarily, if phosphorus atom was able to bind it, it will hover around here and it will not respond to electric fields. It will get stuck. That's a localized electron. But if it has an ionization energy, if the energy state is very close to the minimum of conduction band, such that this is of the order or less than kT, then at room temperature that thing will be ionized. It will get out into the band. And then now it's in the band, and then this phosphorus atom, as a result, once that electron becomes delocalized, it has lost it, so that electron is free to move around in the crystal. This thing gets positively charged, right? It has lost an electron. It was charged neutral earlier, so it has lost an electron. And so if I had, instead of one phosphorus atom per unit volume, I had ND number of phosphorus atoms. That's what we call as the doping density. How many of the atoms of a crystal do we replace with the dopant atom? This is a dopant atom. If it gives electrons, it's called a donor, and if it accepts electrons, it will be called an acceptor. So a donor will make a semiconductor electron rich. An acceptor will make it electron poor. What would an acceptor do? For example, what would I choose for acceptor? Perhaps aluminum. If I choose aluminum, then aluminum has it's on the left, so it's group 3, right? 3. If it's group 3, then it has one less electron, right? It has 3. Therefore, 3 of its electrons can bond, and one of them is missing, right? And that's the hole. And that hole, where should that effectively empty state be? Essentially, it took away a state from here, and it should be very close to here. It's exactly symmetric. And then again, temperature-wise, if that hole escapes, then this thing, if this whole empty state is able to move around now, if it's able to move around and it doesn't get tied up with this, then this aluminum atom will become negatively charged, right? The donor becomes positively charged, ND becomes positive, whereas if I have acceptors, and you can see the reason one might call it an acceptor is this thing accepts, it pulls out an electron from the valence band. It pulls out an electron and it empties it out, and that's the hole. So it becomes Na minus. It gets negatively charged, the acceptor. And the Nd plus ions, it's an ion, and it cannot move in the crystal. It's stuck in the crystal. It's immobile. What is mobile is the electron that came with it. Similarly, acceptor ion is immobile. What's mobile is the hole that came with it. So then the hole is an empty state here, and the electron is a filled state here. And these came from the acceptors, because the acceptor state here, pulled up an electron here. And similarly, this question.
How would you explain the opposite case? If you have like oxygen and silicon dopes at p-type, but it's obviously more electrons in silicon, so there's therapeutic for that.
Say that again?
Oxygen doping in silicon is actually p-type. Counterintuitive from the simple picture because it has more electrons. Is there a good explanation for that?
So this picture is a substitutional doping, and if I just substitute an oxygen level here, let's see, let's say I bring in oxygen, and oxygen has all these atomic levels. Let's say oxygen had a level here. Though it's on the right side, it is possible that it can break this rule that I told you, that it can dope something n-type. But more generally, it is something else. This picture of a shallow donor is not what is in operation in oxygen and silicon. And does oxygen really dope silicon n-type? Because I'm not completely sure about that. It does dope quite a few, 3-5 semiconductors n-type. That's for sure, right? But oxygen, if it is that what you said? I mean, it's n-type, right? If it dopes it p-type, which is if I say that with this oxygen I can get 2 electrons, that one can kind of also maybe possible, right? If it's but p-type is very difficult to explain from this picture. Yeah? So I mean, okay, so there are many ways it could. For example, it does form a complex. Instead of being substitutional site, it forms an oxygen atom, a complex or interstitial site, and then it's possible that the energy dynamics of it is such that there's a state here. It's very possible that way. But if it is substitutional, it may be very difficult to get a p-type. But I can maybe discuss with you later about this and find out. Yeah.
I was always under the impression that it was because there was an energy level in oxygen,
which is
similar to an energy level in silicon. So it
yeah.
bonds to silicon, and that's why it's p-type.
Right. So that's why I say the oxygen, atomic levels can line up such that you can line up very close to the valence band is what I was trying to get to. But these are things that you typically, and it can happen many times in semiconductors. Typically, this is not what I would choose as a good p-type or n-type acceptor donor. What I would choose is the one that is very shallow and it comes with an extra electron either to the left or to the right. That's what I would always choose. But it can form complexes. It can form these resonant states. And if I put phosphorus in gallium arsenide, the state of nitrogen is kind of, or nitrogen into gallium arsenide. It's here. It's inside a band, not even inside the gap. In which case, it splits the band into 2 and all that sort of thing. So it can have many ways of creating the electrons or holes. The one I'm telling you is kind of the simplest, and it's the most used. Okay, so acceptors become charged, donors become charged this way, and yeah.
This question is just about, so we solved for the band structure using like a linear combination of atomic orbitals.
Correct.
How could we solve for the donor level?
I will do that right after second prelim. After the second prelim. This is what we do is we are going to do. This is called the effective mass theorem, by Cohn and Luttinger. We're going to solve it and show that this extra electron state that comes about is just like if it behaves like a hydrogen. This electron and this positive charge behaves like a hydrogen atom, but with slightly different methods. So we're going to show that. I'm going to do that after the second prelim, the full quantum mechanics of it. But at this stage, at least, if it's if it makes sense, what I'm saying, if you choose the right atoms, I can choose a donor activation energy of ED. The state here is ED below, and an acceptor activation energy of EA. Okay. These two, and based on that, I can redo my electrostatics and my charge neutrality now. So let's say I take a crystal and I dope it with ND donors and NA acceptors. Let's say I dope it with both. ND maybe 10 to the power 17 per centimeter cube, phosphorus atoms or donor atoms in silicon, and NA, I don't know, maybe 10 to the power 15, depends. I'm just writing these numbers down, of aluminum atoms as a p-type dopant and phosphorus as an n-type dopant. So now you can ask, where's the Fermi level now, right? And now you can see that it'll be not necessarily in the middle anymore, right? This is a doped semiconductor, right? So now the charge neutrality condition is the following. Total number of negative charges is all the free electrons that you had, that you have in the conduction band. That's the free electron. Those are negatively charged. But then if you have ionized acceptors, Na minus, those are also negatively charged. Now these are not mobile. These are fixed, but they're still negatively charged. Therefore, the total negative charge becomes that, right? And the total positive charge now becomes holes plus the ionized donors. That's your new charge neutrality relation. And what is the expression for N? It's exactly the same as what we had written before, right? The only thing is it depends on the Fermi level, right? And we don't know where the Fermi level is now. How do I find the Fermi level? I solve this equation. So the question is, where is the Fermi level after I dope it? then you solve this equation and get it. So now again, I'll go in and write NC, and maybe my Fermi Dirac approximation, or I write the full-blown expression, half eta, E F minus E C over KT, plus Na minus. Now this is something let me bring up a couple of slides to finish this up. So Na minus will be the doping density divided by 1 plus. Typically there's a degeneracy factor, and then there's an ED over KT. EF. Okay, so there's so it has its own Fermi function sort of thing, is equal to hole density and V F half. I'm just going to, so essentially you have the acceptor density here, you have the donor density here, and then there's a 1 plus some occupation function and an exponential here. The thing is, in this equation, you know everything except you know what is the ND, you know what is NA, you know this, you know that, you know the bands and all that. The only thing unknown is EF. Right? So you have to solve it. And generally, it's not analytically solvable, again, this full-blown equation. But if you make these little approximations that we did earlier, Fermi Dirac and all that, you can typically solve it. Okay? So let me just show you the exact form of it. Where is the, okay, blank screen. Screen down. Wait, where did the doping go? All right, so I'll come to the exact quantum of picture of this later, but essentially at this point, this is what we're kind of talking about. If again, I talked about silicon, but if you had a gallium arsenide crystal, and this is gallium, and you replace it with silicon now, so silicon is to the right of gallium, so that's also an N-type donor. And here are kind of the states that I was mentioning. These are the states that form. And I'm going to get to the physics of it later, but here's essentially the ionization statistics. So if I want to find Na minus or Nd plus, this is, these factors look like the Fermi Dirac distribution 1 over 1 plus something, but there's a factor of 2 here that comes from the fact that I can't have 2 electrons in the same donor site. It's because of Coulomb or Hubbard repulsion, you can't have it, so you get this factor. Anyway, this is the factor that I was writing over here, this thing. So that's really that factor here. Okay? Instead of an exact straight Fermi function, the Fermi function would be there's no 2, it's 1 over 1 plus e to the power this. But this 2 comes about because of this Hubbard and some aspects of degeneracy, and similarly for Na minus also. So, right? And now when you combine these and you write these together and write your whole charge neutrality equation using this, then you can find where is the Fermi level. And I'm going to just, this is your assignment problem number 1 currently, where you are given a situation where you have both N and P type doping, but the activation energies are not quite the same. One of them is very deep activation energy, and you can set it up, just means ND and NA, NP, all that stuff, beta, and essentially now I can, for any general semiconductor, I can go in and say that plot me the following things. I have 4 terms here, N, P, Na minus, and Nd plus. Right? I can plot N and P as a function of where is the Fermi level inside the materials. Remember, N and P, electron density and hole density, don't care exactly whether you have doped it or not. That expression just depends on the Fermi level. So here's my electron density. If my Fermi level, here's the gap of a semiconductor, 3.4 eV. I've chosen this. And here's where, if my Fermi level was at 3 eV, then here's my electron density N. My electron density would be, about about this much if the Fermi level was here. If the Fermi level was very close to the band edge in the conduction band, 3.4 eV, I would have roughly 10 to the power 19 or 10 to the power 20 per centimeter cube carriers. So that's my N. If my Fermi level was close to the conduction band, which is on this side, I have very few holes. This is my hole density P, very, very few holes. But if I move my Fermi level to the left, this is the hole density, and it rises exponentially. And if my Fermi level is very close to the valence band edge, my hole density is extremely large, 10%. Right? So these are the two terms, N and P. And the other two terms, the red line there is a plot of this quantity, the total negative charge. The total negative charge. This is N plus ND. Sorry, N plus Na minus. It's the sum of the two. And the Na minus, therefore, you can see it goes like that and then flattens out. And this is your curve. Similarly, the blue is the total positive charge. Right? The total positive charge. I'm just kind of plotting all the parts of this equation. So maybe you can tell me where's the Fermi level now, right? It's when the total negative and the total positive charge meet, right? That's where the Fermi level is. Therefore, in this picture, it's right here. Right? It's heavily N-type. And the reason for that is I have doped it intentionally with a lot of electrons. ND is very high, 10 to the power 20. And so let's reduce the electron density. You can and this is to the right, I'm reducing it. And let's increase the hole density. And you will see that this curve starts moving back here. As I increase my hole density to 10 to the power 20 or so, the Fermi level, which is the point of intersection of the two, kind of moves from here to there. So that's holes. So that's the whole the complete picture of a bulk material and its doping. One of the very important, and this is something I've asked you to plot also in your first assignment. Sorry, in the first problem of the current assignment. And here I put in the donor and activation energy. This is kind of a very general result, so you can set it up too. And if there's any other problem later, you can use it. Another very important result is NP is equal to Ni squared. Still holds whether you dope it or not. I mean, when you dope it, NP is still equal to Ni squared. So in the I didn't get to the transport part, but I'll get there, I think, on Tuesday. And I think we'll kind of have to end the class now. I know that the assignment has quite a few transport problems, but some of the early ones, let me see. Next Thursday, we don't have a class. I'm traveling. So I would like to have a makeup sometime. Sorry, not next Thursday. This coming Thursday. This coming Thursday, I don't. I'm traveling. I'm away. So we have only one class for your prelim.
Next Thursday is prelim.
Let's see. So can we? We had done an extra class on Friday last time. Will that work this next week Friday? So instead of having the exam on Thursday, we can have it on Friday, if that works for everybody or not. So.
What time was it done on Friday?
What was it? Oh no, we had it on Thursday.
Yeah.
We had it on Thursday, right?
Night?
Thursday, 5 p.m. or so. We had that last time. I'm saying.
We can have it on Friday if everyone.
Well, depends. I mean, if people are available and all that. Sorry.
That's the only spring break.
So,
Spring break is on Saturday, so if someone is traveling on Friday evening, then.
Right. Yeah.
What lecture is this prelim up to?
Really depends. So when we have the prelim. So if we have it on Thursday, then perhaps till today. But if we manage to delay it, so yeah, we can keep it till today. So let's just keep it till whatever we cover today, and that would be problem 1 of your current assignment 2. I mean, kind of till there. But we do need to make up a class, so I'm missing it this Thursday, and I'll contact you then and by emails, and we'll find out. So Thursday afternoon still work? Thursday 5 to 6:30 or something like that? Will that be okay, Thursday? So in that case, what we'll do is we can have the normal class on Thursday, and then have an exam in the afternoon, if that works for you. No? We'll just poll and see if it doesn't, then we'll take care of that. So, yeah.
I'll send out the post.
That's all next week. All next week.